Good evening, my lovely physics guys and gals. So today's worksheet I gave you in class, so you want to have this worksheet out in front of you. And what I'm going to do is actually go through a couple examples. So I got 2 examples on here. So tomorrow in class, we're going to use these examples to do other problems just like these. So I'm going to do one that's elastic and one that's inelastic, just to show you the difference so that you have both options. All right, so I'm going to go ahead and get rid of the video for now. All right, so now the video is gone. We're going to look at this worksheet so that we can see how to do these problems. So first of all, it tells us that anytime we have a system with forces acting on it, our total initial momentum is going to equal our total final momentum. This was something we learned during our car collision lab. So regardless of it being elastic or inelastic, this car collision lab, we learned that our momentum is always going to be conserved. So that's our basis for this worksheet. So when one object hits another object, the momentum that it carries with it will transfer to that other object. So first of all, think about when we do these are sort of like bar graphs. Just like what we did with numbers with our car collision, we're just going to look at the same thing in just a different way. So let's go ahead and let's look at our first example. So I'm just going to move it up here out of the way so that we can see what we're working with. So for our first example, let's say we have a 90-kilogram hockey player. He makes an illegal check by ramming an 80-kilogram player at 6 meters per second and slows down to 4 meters per second after the collision. The 80-kilogram player was traveling at 2 meters per second towards the 90-kilogram player, and we want to figure out the velocity of the 80-kilogram player after the collision. So I'm going to move this down here just so that I can write a few of those key pieces of information. So first thing it tells us, our 90-kilogram player was initially going 6 meters per second. It tells us then he hits into another player and he slows down. Let's just double check. He slows down to 4 meters per second. So that's our first one. Then it tells us that our 80-kilogram player, I'm going to use a negative sign because it tells us that it was heading towards the 90-kilogram player. He then gets hit, and we want to know how fast is he traveling and in what direction. So listed below then, we have 2 different things. We have initially what happened and finally what happened. So first of all, when it says mass, we're going to put our 90-kilogram mass there. The object, we can call it player 1. So I'll call him player 1. And his initial velocity was 6 meters per second. So over here on the final side, he still has the same mass. We'll keep him as player number 1. This time, though, his velocity has slowed down. So what we're doing on the bar graphs, we always want to start our bar graphs at the 0 line. Think of 0 as that's where we start. If we're heading in one direction, we can make our bars this way. If we're heading in another direction, we would draw our bars going the other direction. This type of look, this type of bar graph is only qualitative. So being qualitative, I don't need to know exactly for the graph purpose what specific number I should go out to. Notice there's only 4 lines here. So I'm going to say that 6 meter per second player, I'm going to have my bar graph go out 3 lines. Let's say then when he's done, this over on the right-hand side, let's make it go out 2 bars, just to show the bars that he got a little bit smaller. So now I have to fill in the information for my other player, my player number 2. So my other player is a smaller guy at 80 kilograms. We will call him player number 2. Direction does matter. We need to make sure that we put 2 meters per second in the negative direction. So I'm going to fill in my bar. Notice I'm going from the 0 line, and he's negative, so I need to show him going the other direction. Then my 80 kilogram, my player number 2, this is one where I don't know his velocity. So in that case, I'm not going to have a bar. Whenever we have 2 things hitting each other, just like we had said, just like we learned from our car collision lab, momentum is always conserved. So if I add the momentum of player 1 plus the momentum of player 2, it should equal the momentums of each of those players at the end. So think about this as we're going to add player 1, their momentum, plus player 2 should give me the same thing at the end. Player 1's momentum plus player 2's momentum. So for our conservation equation, our player 1 initially started at 90 kilograms times his velocity. Remember, our momentum is mass times velocity. So I'm going to take 90 times 6 plus 80 times, don't forget the negative signs. They are very, very important. It will show us the direction, but we have to put them in here. So our player 1 on the other side should be 90 times 4, plus our player 2, we don't know his final velocity, so we'll leave that blank. So in this case, let's say we wanted to figure out how fast is that guy going at the end. Well, now I'm just solving my algebraic equation. So on the left side, I'm going to get 540, that's this number, minus 160, because that's my other number. So I'm going to get 380 on that side is equal to 360 plus my 80 velocity final. So I'm going to move my 360 over to the other side. This is adding, so I need to subtract it. So I'm going to get 20 equals 80 V final. Now all I'm going to do is divide by 80 to get it over to the other side. And we notice that this player number 2, he's going much slower. So he was going 2 towards the player. Now he's only going 0.25. But notice, the sign that we got for this is positive. So that means player number 1 hit player number 2 with enough force to make him change direction and actually gave him a little bit of a velocity. So it changed his velocity, changed his momentum. He was negative. Now he's a positive 0.25. So that's how we would use these bar graphs then to help us solve pictorially our problems. So let's look at one more example. So let me pull up my example here. Come on. There we go. All right, for my last example, we have an empty train car traveling at 4 meters per second, hits another fully loaded train car, and the 2 cars couple together. When a train car couples together, think of that as it stuck together. So our last one was a bounce because the two players hit and bounce apart. This one, the train cars are actually going to stick together. So it tells us that an empty train car is 4,500. So I have a 4,500 kilogram car. And it was initially traveling at 4 meters per second. And it also tells me then that it just hit a fully loaded train car. So that other train car, it doesn't tell us it was moving. But it does tell us that that train car weighs 3,500 kilograms. I'm going to call this empty car and full car. So initially, this one was just sitting still. When they get coupled together, we have to add their masses together because now the system is moving as if it were one object. So we're going to add the two masses together. So we get 39,500 kilogram. And you can think of this as car plus car now. So we want to know how fast are those two cars stuck together going to move. Same thing as we just did. We're going to use our momentum conservation equation. So we're going to take our 4,500, which was initially moving at 4 meters per second. We're going to add to that our empty car, which was 35,000 times 0. That should be equal to our total mass, since our cars are coupled together. And we want to know what is our final velocity. All right, so we want to solve for our final velocity to figure out again how fast is our cars going now that they're stuck together. So this part here will cancel out because that's a 0. So our 4,500 times 4 gives us 18,000. That's equal to our 39,500 times velocity final. To solve for my final velocity, I'm going to take my 1800 and divide by my 39,500. So the final velocity, once those cars hit together, 0.46 meters per second. So if I go back up, oops, I forgot to draw the pictures up here. So I'm going to just draw the sort of 0 at the darker line. I'll make my 4 go out 2 boxes here, shade it in. And so then my final velocity is still in the positive direction. Notice this came out to be a positive number. Much smaller though, so I'll make those two combined cars, their bar, a whole lot smaller. All right, hopefully that will help tomorrow. And we'll work on some more of these problems, just like these. Your worksheet 3 that we're going to be doing in class is just like these practice problems. So if you have any questions, definitely ask as you're working through them in class. All right, I will see you guys later. Have a good evening.